Hello, everybody. This is Chad Hens, and welcome to the SNIA Ethernet Storage Forum Break Talk presentation for today. Today we're continuing our series on everything you want to know about storage, but we're too proud to ask. This series, we're going to go through part turquoise, where does my data go? So before we get started here, just a little housekeeping. Please keep in mind that today's material is copyrighted by SNIA, unless otherwise noted, and that this presentation can be used by SNIA members in presentations and literature as long as SNIA is acknowledged and it's reproduced without modification in its entirety. As typical with these presentations from SNIA, we will be making this presentation available in a follow-up blog on the Ethernet Storage Forum section of SNIA.org website. URLs and addresses will be provided at the end of the presentation today. Also, we encourage you to ask questions during the presentation. We will hold a Q&A section at the end, but we often run out of time to go through all of them. We'll be combining all the questions into a separate blog article to be published soon after the presentation is completed. So who are we? I am your host, Chad Hens. I am a member of the SNIA Ethernet Storage Forum and a principal SC at Cisco, and I will be the MC for today's presentation. We do have an esteemed group of presenters, and I'll go over in the order that they will be presenting. So we have Scott Shadley, who is a principal technologist for storage technologies at Micron. We have Rob Peglar, who is an SVP and CTO at Symbolic IO. And last but not least, my colleague Jay Metz, who is on the board of directors for SNIA, as well as a research and development engineer for advanced storage at Cisco. From a standpoint of SNIA, just to give you an understanding of SNIA at a glance, is that we have 160 unique member companies that participate in SNIA. We have over 2,500 active contributing members and over 50,000 IT end users and storage pros worldwide that are as part of the SNIA organization participating. From an agenda standpoint, we're going to start off with Scott going over different types of memory, in particular the differences and use cases of volatile, non-volatile, and persistent memory. Next, Rob will go through the architectures and form factors used for memory and storage in the enterprise, with a little bit of decoding of the acronym suite. Lastly, Jay will be going over NVMe and NVMe over fabrics, and how this impacts and plays into connecting these architectures. So with that said, let's go ahead and get started. And I'm going to hand it over to Scott to start us off. Scott, take it away.
All right. Well, thank you all for attending. I appreciate your time in whatever time zone you happen to be in and are setting aside some time to listen to us chat. So for this section, I'm going to cover, again, the three types of memory technologies that exist today. Having a device physics background gives me some opportunity to dig a little deeper into this and hopefully keep it at a level that makes sense for the folks online. And throughout my section, I'll actually be introducing some of the alphabet soup or acronym soup that you'll later hear Rob kind of decode for us. So we're going to do this kind of in partnership. So again, encourage you to ask questions. We'll get to them as we can as the Q&A section, or of course afterwards if needed. So we wanted to kind of keep it a format for this section where we give you some definitions and then some examples for each of these technologies. So for volatile storage, there is a SNIA definition for volatility. And it basically comes down to a way of describing a media technology. In this case, DRAM is the most common version that people are aware of in the market. And when you pull power from this product, it loses data. So therefore, it's volatile. It only exists as long as you maintain status quo. As soon as you turn off the ability to keep it live, whether through power or from some other issues with the system, the data is lost in the drive or in the memory technology. And in most cases, we use the term refresh the data. So at the end, what does this mean to us as far as the technologies that we're dealing with and how they're built and architected? Computer memory, as we know it today, memory modules are volatile because they use a capacitor. So much like if you plug in any modern day PC charging cord, there's some kind of indicator light on the cord noticing that it has power. The larger the wattage of that particular power adapter, the longer that once you pull it from the wall, that little light stays lit until it actually goes away, because they're using capacitors inside that power adapter brick to transfer from alternating current to direct current. We do similar things with volatile memory. You can see here on the right side of the page, there's two different modern technologies that are used today by different people because there's patents involved in IP. The one on the top is considered a vertical capacitor, and you'll see the capacitor itself, or the cell that's used to store the data, is the rough or bumpy looking surface, and that's intentionally done to create more surface area to allow us to refresh the device less often, therefore allowing us to have better throughput or performance. And since we do it as a capacitor, we use the terms charge and discharge for the same concepts of writing the data. So we charge or we write a 1 into the capacitor and store that information. As long as we maintain power to that capacitor, it stays a 1. We can rewrite over that data or discharge the cell instantaneously, and therefore it allows us to have much more flexibility of our data. The lower one, you can see we actually etch or dig trenches, or what's called a trench capacitor, to fill with the same type of material to store that charge. Either one of these technologies, because the storage node, if you will, the part of the cell that's holding the data is directly attached to the substrate of the silicon. When you pull power, it drains out and disappears into nowhere, if you will. So volatile storage from that perspective is very fast to read and write because I'm charging or discharging a capacitor, and you can charge and discharge capacitors very quickly, and each capacitor is individually managed. As you can see shown in the diagram at the top where it says SDRAM cell, each one of those capacitors is individually managed. So it gives us some very good throughputs, and that's why we put it so close to our processors of today. So if we now move into the next level of material, that would be called non-volatile storage. Non-volatile storage, as SNIA defines it, is an electronic device that is preserved even when power is removed. Again, another way to look at that is we use terms program and erase for non-volatile memory because it's something that can be done once it's powered and then power is removed, you do not lose the data. And examples of modern day samples of that are known as flash or NAND devices, and you see them in SSDs, USB cards, micro USBs, and everything else that has some form of boot up sequence that's required, whether it's a cell phone, your latest wireless security camera, those types of things. And those are considered non-volatile storage. And there's multiple versions of those, and again, Rob will explain a couple of unique versions of it. But at the device physics level, or at the actual bit-to-bit level, a non-volatile storage device is programmed, not charged, like a volatile memory cell is. So the state of this is actually looking at it from a completely different perspective. You can see on the right, there's the design of, at the very top, a standard transistor. So for a transistor to work, you have a gate that opens a channel between the source and the drain. And to do that, you apply enough power to the gate that it overrides that transistor's capability to block it, and it allows the data to be read. What we do with a non-volatile device, whether it's NAND or NOR, is we insert a floating gate below that gate that allows us to store or program electrons into that floating gate. And it basically allows us to generate what's called a voltage adjustable transistor. So if I want to program the device, I actually program and place electrons within the floating gate that prevent the ability for a device to be read from the source to the drain. And that's why in volatile memory I can write or I charge up to a 1, but in a non-volatile device I actually program a 0. And that's one reason why it's called a NAND or a NOR, the not part of it. Because I'm not actually writing the 1 to the device, I'm writing a 0 in the way of a program. And when I erase it, I'm removing those electrons, and therefore the path opens, and since the path completes, you get a 1. So it's something in the way of a very unique architecture, but what makes this non-volatile is, you can see, we call it a floating gate for a reason. It's not electrically connected to anything. There's some device physics technologies and terms that are used to create the electron transition across that barrier. Fowler-Nordheim tunneling, for example, for those that would like the discrete description of it. But it basically is an ability to transfer electrons through a closed path and allow them to reside in that particular location. Now, this does cause some physical damage to the device, so that's why over time, even a non-volatile device in the form of a NAND or NOR has a finite life to it. What the benefits here is it's still very fast to read, but because of this electron tunneling and this technology that we use to do that, it creates a long program time. So when I'm writing data to these devices, it forces us to spend more time articulating that movement of those electrons than in just charging a capacitor. So it's not nearly as efficient in the getting the data in as it is getting the data out. And that's why, for example, this does not directly replace what we get in the way of volatile storage or volatile memory, because we need those speeds in order to be able to accomplish some of the tasks that we're working to do. So when you have volatile, you charge a location to a +1, and in a non-volatile, you program or you write electrons in to create a 0. We are seeing these used mainstream today, NAND, NOR, SSDs, and then DRAM, of course, on the other side of it. Now, what's coming next is what we classify as persistent memory. Now, persistence, as defined by SNIA, is a synonym for non-volatility. So persistent memory is the idea of trying to combine the best of both worlds. Take what you get from volatile memory in the way of DRAM in looking at it from a speeds perspective, but providing the users a non-volatile state so that when we pull power from it, it's still active and the data is still there. So my simplified definition is a material used to store data in an alternate state of the material. Because as of today, all of the persistent memory solutions are not based on charging a capacitor or programming a floating gate. They're actually based on changing the state of the material that's being used for them. So some of those common terms today exist are MRAM, 3D crosspoint, resistive RAM, and spin torque or STT-RAM. Now, again, there's smaller deltas in the read versus the writes, but they're still not as fast as volatile memory. So this gives us some challenges when it comes to the ability to replace any of the existing architectures today. So it is truly a new segment. Oh, sorry, guys. So examples of these, again, it requires a physical change to go from a 0 or a 1. So whatever the status or traditional state of the material is can be defined as a 0 or a 1. And then when the state is changed, it can then be turned into a 1 or a 0 alternately. Most of these technologies, and some of them are shown here, and it'll be easier to read probably when you get the PDF. Anything from carbon nanotubes is another far-reaching version of technology. But these products, we have probably roughly about 30 or so different technologies that are existing in the markets today, but none of them have had the scale capability that we're looking forward to that we get from the DRAM, the NAND, or even to some extent the crosspoint that was recently announced. And also the concept of true persistence is still not clear. So we know that if we pull power from these devices in the engineering labs that they're being developed in at the scale they are currently, they're persistent. The data does not go away when you pull power, and you sit it on a shelf and you go back and look at it a few months later, the data is still there. But because none of these have been put into a true manufacturing environment and driven to the levels of success that we have with things like NAND and NOR or even DRAM, and knowing the constraints of them, the true persistence of them is still truly unclear. So we do have a lot of work going on there. It is something that's coming and will be a kind of a forward-looking technology for us. So if we look at these across all the different scopes of how they're being used, and you can look at the bottom where we have volatile, persistent falls between volatile and non-volatile. We continue to fill in this gap that the world is creating between the CPU, which would sit on the far left of the page, down to the hard drive or magnetic storage that we all love and or hate that exists today for data storage. So non-volatile storage has come out in the way of SATA and SAS SSDs. We have NVMe-based SSDs, and then we get into the DIMM-based products. So what's shown here on this particular page, you can see on the left, it's the fastest to read to write, but because of the architecture, it doesn't allow us the densities that we need to make it viable on a scale that would make it a storage-friendly like product. And also because you lose power, you have no data, it makes it very hard to store information in one of those products. If we look at the persistent band, we're seeing things like NVDIMMs, and there's now multiple versions of NVDIMMs in development or in production, and they're called NVDIMM N, NVDIMM P, there's an NVDIMM F. And again, you'll hear some more definition on those from Rob. These are very fast to read. They're still slower than a DRAM or a traditional DIMM, but they are now at a point where they actually maintain data. And then there's even the Optane SSDs that have been released that are based on 3D Crosspoint from Micron's partner that are available as well. One thing that you'll note is that as you move through this from top left to bottom right, there's a number there showing how fast that product can be. Some of that is actually gated by the media, and some of that is actually gated by the interface. So when you get into the non-volatile brick, or the blue section of the page, this is our mainstay of storage, what we call fast storage today, but a SATA drive is limited by the interface, not by the media technology. And that's why we see the market driving such a very huge direction change. And you'll see from both Rob and Jay what NVMe does for us in that space, because it starts to allow the media to shine and not have the interface gated. And this goes all the way back into the days of, even if you really want to get fun, to SCSI and to PATA, or parallel versus serial ATA. And then, of course, everybody continues to ask, will we ever replace non-volatile storage products over magnetic storage? We're going to continue to see that magnetic storage footprint drop, but all of these technologies still have the limitations or scalability concepts that still allow us to have all 4 variants of this product technology exist long term. So if you need something really fast and not necessarily high density, and you're okay with the data being stored somewhere else, you go with a volatile memory solution, and today we call that memory DIMMs or RDIMMs or LRDIMMs based on DRAM. If you need storage, you tend to look at fast storage in the way of non-volatile products or slow storage in the way of magnetic. And as the products and availability come out, you get to start spreading the wealth with persistent storage solutions on both the memory side as well as the storage side. So again, these technologies will continue to develop. There's not really any one product that's in development today that will finitely replace what we have in scale today for any of these solutions. And I guess that's kind of the nuts and bolts, is we all would love to see something new. We like playing with new toys, but it's also always good to make sure and stick with the products we know work well and can be maintained in that way. So volatile to non-volatile to persistent. Hopefully that was a brief and yet useful introduction to the different memory technologies at a device level. So at this point, we'll go ahead and move forward, and we'll let Rob take over and do some alphabet soup.
Thank you, Scott, and thanks everyone for being on the webcast. Here in the eastern and central U.S. at least, it's around lunchtime, so why not dive into some tasty alphabet soup? I think it'll be very good. And you might learn a little something too. So let's talk about all these crazy acronyms and abbreviations here that we in the storage industry like to throw about. So let's start somewhere. And I think the somewhere, if you think about a taxonomy or a categorization of these types of materials, as Scott gave us a good overview, you just heard about all sorts of different forms of memory, but how do they actually work in practice? So let's start with the first thing that we typically think of as memory, and that's called RAM. And RAM stands for Random Access Memory. Fundamentally, though, one of the big differences between RAM and other forms of memory is that it's byte addressable. So it's typically tied to a processor of some sort. We all know about CPUs, but there are other forms of processors that RAM is also tied to. And this may be within the device itself. As a matter of fact, not necessarily over an explicit channel. Now, the most familiar form of RAM, although there are several forms, is called DRAM, and that is dynamic RAM. Scott mentioned that this involves charging and discharging of capacitors. He gave you a good overview of that. And this DRAM is typically deployed in a form, or a form factor, if you like, called a DIMM, D-I-M-M. It stands for Dual Inline Memory Module. And again, these are the most familiar manifestation of RAM. We see them all over the place. They're very prevalent in, of course, servers, but also laptops and desktop computers. And DIMMs have been around for a long, long time. But they are also typically deployed in smaller form factors that are in non-DIMM form, in all sorts of different environments, in particular in mobile and embedded you'll find DRAM a very ubiquitous material. And again, as Scott said, this is a volatile memory. So let's talk a little bit about flash. Everybody likes flash, and we can get flashy with it if you like. In general on flash, it is a non-volatile form of memory as opposed to DRAM, and Scott gave you a briefing on that. And there are two different types depending on the circuitry that's used inside the device itself. One is called NOR, one is called NAND. And if you know your electric circuits, you know what that means. And in fact, the handy little diagram on the right is an example of a NAND circuit. Now, NAND is, again, a very ubiquitous material these days. It forms the fundamental technology for lots of different devices. We'll talk about some of those and their alphabet soup as with it. And NAND in particular is interesting because it is a block addressable form of non-volatile memory. So you cannot address it by an individual byte. It doesn't work that way. It works on a block basis. And in fact, NAND is further organized blocks into what they call pages. And as Scott mentioned, erasing and writing NAND involves operating on a page level. And then and only then, when you erase, can you write in new data. So that's, again, why NAND has the characteristics that it does. And these cells, indeed, do have a finite life cycle. We like to call them program erase cycles. And it's important to know what the program erase cycle count is, especially in an SSD, which we'll get to in a minute. It's very important to know what the reliability is and the longevity of such a device. Now, there is another type of flash that you may not have heard of called NOR, and it's quite often found in embedded devices, in particular these days in automobiles. It's not nearly as dense as NAND, and fortunately they don't need a lot of it in these embedded applications. And it's relatively more expensive than NAND. One of the reasons why is because you can actually execute instructions out of NOR, so you can put your code in NOR, whereas in NAND it's a block device typically used for storing data and not necessarily instructions. So again, lots of different forms. What we know most often is NAND, and NAND is, again, a very ubiquitous material. It's found in all sorts of different devices. All right, so let's talk a little bit about bits. And what's all the fuss, if you like, about the bits per cell? You may have heard that about NAND. And yes, there are lots of different types of NAND just within that category itself. So let's talk about that a little bit. It turns out, pun intended that is, it turns out that there are four general categories of how many bits are represented in a cell of NAND, starting with the number one. So single level cell, which was the first form of NAND produced by the manufacturers, quite literally 1 bit represented per cell, and we represent those bits as voltage levels. So we have 0 and 1. That means we have 2 voltage levels, nice and simple, relatively straightforward, and as it turns out, relatively fast as well, switching back and forth between those voltage levels pretty quick, and lots of program erase cycles compared to other forms of NAND. But the downside is, since I'm only representing 1 bit per cell, it's not as dense. In fact, it is the least dense form of NAND. It has been around for quite some time, over a decade now, very much in use in the highest of the high-speed devices that use NAND. And then going down the chart, we have multiple level cell, and it was called that several years ago because we wanted to represent some other name than single or double, so we used the word multiple, and that's what it's known as today, is MLC. And in fact, it is 2 bits per cell in the most common representation, which means now I have 4 different voltage levels representing all combinations of those 2 bits. Now, what happens in practice with MLC is that it becomes slower to do the program erase than a single level cell would, because now I have to represent 4 possible different voltage levels. But on the other hand, it's more dense than a single level cell, so you get a twofer with MLC. You get relatively fast program erase, and you get relatively dense. So this is a very popular form of NAND. Again, it's been around for quite some time. lots of devices, and including today, still made out of MLC. Now, more recently, in the last 7 or 8 years, the NAND industry has developed TLC, or triple level cell. And by now, you probably get the, the gist of the program. I have 3 bits represented in a cell, and hence I have 8 different voltage levels representing the combinations of those 3 bits. Now, you do pay a price for this in terms of speed. It is slower than MLC and quite a bit slower than SLC with fewer program erase cycles. So over time, it is less reliable than the other forms of NAND. But on the other hand, it's denser. And it is very popular today because on a per bit basis, it is relatively inexpensive to have devices made of TLC. So this is quite popular now, and you see a lot of new devices, in particular SSDs, made out of TLC NAND with 3 bits per cell. And again, fairly cost-effective in terms of NAND. Now, the last step, which is actually not on the market yet, but is under development, is a technology called QLC, and I'll bet you can guess what that is. Yes, indeed, 4 bits per cell, 16 voltage levels, so you get the drift here, even denser than all the other forms, but also even slower than all the other forms, and with fewer program erase cycles in that material. But QLC represents a very interesting aspect of the industry now. Extremely dense devices can be made with QLC NAND, and I think you will start to see those devices come out in the next several months and years as we continue to develop that. So 4 different categories, actually, of bits per cell in a NAND device. All right, moving ahead. So let's get vertical here and talk about 3D NAND, 3-dimensional NAND. How can there be such a thing? We all are familiar with chips being flat, so what's this stacking or layers sitting here inside a chip? And this is a relatively new development within the past few years, I would say, and 3D NAND is very much like its 2-dimensional, or what we call planar NAND, but yet it has multiple layers. So the handy little graphic on the right, you can kind of think of it as a skyscraper with multiple floors, and of course lots and lots of elevators between those floors, because literally all the NAND circuitry on the inside has to talk in amongst itself on all the layers. And each layer, of course, has a certain capacity depending on the number of bits per cell, and there are variants, typically MLC or TLC for 3D designs, and you might see anywhere from 32 to 48 to 64 layer NAND being produced today and on the market. And then projecting out, you might even encounter 96 or 128 layer. This is what the industry is pointing toward. I wouldn't be surprised at all in the next few years to see this many, many layers of 3D NAND being produced. Again, perhaps in even QLC form. And again, 3D NAND is quite popular today. It's very excellent for use in dense deployments. And again, because of the vertical nature of the 3D NAND, you can get now denser material even in a relatively small form factor. So I think, and I think the rest of the industry does as well, that 3D NAND will really be the basis for a lot of new future products using NAND, and again, as opposed to planar or 2-dimensional NAND. So that's what 3D NAND is all about. It's effectively a vertical embodiment of the NAND cell. Okay, so now for our friend, the SSD. We all think we know about SSDs, and in fact, there is a ton of knowledge out there about SSDs, but basically it stands for solid state disk. And this is as opposed to our longtime friend, the rotating or hard disk drive, the HDD. So this is an SSD, and we refer to them as such and have for several years. Now, typically, SSDs do indeed use NAND for the persistent media. If you literally cracked open an SSD, you would see NAND in there. But guess what? You might also see a little DRAM in there, acting as a volatile cache to increase the speeds of reads and writes coming in and out of the device. Almost always used for a write cache. Some SSDs use DRAM for a read cache. When you buy an SSD or integrate one into a server or a laptop, you should check to see whether your SSD actually has DRAM inside of it. And then, as Scott mentioned, there are many other forms of persistent memory that are either coming about very soon or will in the next few years, I think. And it is very possible that SSDs, at least for the persistent layer inside an SSD, will be made of that material. In fact, we have seen the first of its kind. Scott mentioned it, the Optane branded drive, which uses 3D XPoint as the persistent layer. So you will see a spreading out, if you like, of the SSD portfolio from lots of different vendors as the years go by because of the forms of persistent memory that are being used. Now, again, SSDs come in all types of flavors and performance points, capacity, reliability, endurance, you name it. You can really kind of pick and choose the SSD portfolio very wide today. And in fact, they've surpassed the density now of hard drives in the same form factor, be it 2.5-inch, or there are even 3.5-inch SSDs on the market, which are extremely dense, many tens of terabytes in capacity. So again, they have SSDs are now denser than their cousins, the rotating drive. And they also come in all sorts of various form factors. So not all SSDs look alike. They certainly don't behave the same, as we know. Again, because of the wide variation in price points and reliability and performance, and you name it, you can really pick and choose the SSD that's right for your needs. Now, some of the more popular form factors are the fairly ubiquitous 2.5-inch form factor. Again, rotating drives came in 2.5-inch for a long time. Guess what? SSDs do as well. And they have what's called a U.2 connector, which is good for SATA, SAS, and then there is an ongoing connector, which will involve NVMe as well. Jay will talk about that in a brief time. So 2.5-inch SSDs, very popular, very common, available in all sorts of different parameters. Then there is a newer form factor called the M.2. You may not be familiar with this. I call it the stick of bubblegum drive because quite literally that's about the form factor it looks like. It's relatively thin. And it typically is deployed with either a SATA interface, again, long time, well known, or an NVMe interface, which Jay will describe for you. And these are becoming quite popular now because they're relatively small, but yet they can hold a relatively good amount of capacity for their size and for the amount of power that they take. So M.2s are very popular, especially in laptop form. M.2s are quite common now. Again, because they're relatively small, but yet they can be made to act relatively quickly with an SSD. Now, there is one more category of an SSD that you may not be aware of, typically found in server deployments, and that's in what we call an add-in card form factor. Another term for this is half height, half length, which describes the physical attributes of the card, literally how large it is. But SSDs for quite some time have been made on these cards, which do fit in PCI Express slots, again, typically deployed in a server, and also very typically deployed as NVMe devices, as opposed to SAS or SATA. Again, the NVMe will be described by Jay, taking advantage of the PCI Express bus throughput, which is, again, typically found in server deployments only. So, again, various form factors for SSDs, very diverse population, lots of different types. So SSDs are indeed really replacing hard drives in particular in lots of different deployments. But I think we're all pretty much aware of that. Okay, last but not least, let's talk about this funky thing called an NVDIMM. And as you might describe, there are really two parts to this, quite literally. NVDIMM stands for Non-Volatile DIMM. This is as opposed to the DRAM DIMMs, which are volatile, and again, DRAM on a DIMM form factor. Well, guess what? This is now non-volatile memory on a DIMM form factor. So they exist on the memory channel, just like their cousins, the DRAM DIMMs. And as Scott mentioned, there are actually three types as defined by the industry body known as JEDEC. One is called the -F. It's composed of all NAND, so NAND on a DIMM. And then the most popular one today, and the one finding its way into server deployments, is called the Dash N, and it's half DRAM and half NAND. That's actually what's depicted in the little graphic above there. We'll talk about that in a little bit. So it's half and half, equal amounts of DRAM with NAND on the same DIMM with a controller and, of course, firmware. And then the Dash P, which, truth be told, there are no deployments of this widely in the industry, but it is under development. It's a fairly small amount of DRAM and a fairly large amount of NAND. So it is an imbalanced configuration, mostly with NAND. And also it may come in very handy in future deployments. But again, don't worry about the Dash P yet. It's still under development. And the F-type NVDIMM is a block addressable device, so keep that in mind. And the N and P type are byte addressable. So just like their cousins, DRAM DIMMs, and NVDIMM-N, again, by far the most popular deployment today. They are byte addressable. They look like memory because they are memory. They are half and half DRAM sitting on a memory channel. So the NVDIMMs today are the first really example of persistent memory. Now, how do you make DRAM persistent? After all, it's not, right? It's a volatile form. So this requires a little engineering, and we have done the work in the industry to deploy these things called supercapacitors. Batteries might have been used in the past, but battery technology is not really suitable for this for lots of different reasons. So the manufacturers now are making supercaps, as we call them, to ensure that the data in DRAM is persisted into the NAND side of the NVDIMM, even across power loss. So this takes special circuitry to do it. There are some, including my own company, which have done the work to make NVDIMMs work. So you will start to see these, and especially in the latter half of this year and into next year, more and more platforms, typically servers, but who knows in the future where we might see NVDIMMs, but typically in servers, you see more platforms today being advertised as NVDIMM supporting, right? So keep your eyes peeled for more deployment of these funky things called an NVDIMMs. All right, so wasn't that fun? I hope you enjoyed your alphabet soup. And you'll certainly see more of this when the PDF becomes available. But now, for some real fun, I'm going to turn it over to my colleague and fellow SNIA board member, Jay Metz. Jay, take it away.
Oh, thanks, Rob. Actually, before we do, Chad, are there any questions that you want to answer while we have the opportunity, or do you want me to just go straight through this?
Sure. We just have two quick questions, actually for Rob. So the first one is SRAM still used today?
That's a great question. The answer is yes, although it is very rare you will see SRAM deployed on a DIMM. Where you do see SRAM, by the way, stands for static RAM as opposed to dynamic RAM. So SRAM is actually used as cache or a volatile memory space inside of processors. So if you know your CPU architecture, you know they have several layers of cache, typically layer 1, layer 2, layer 3, L1, L2, L3. Those are typically made of SRAM. SRAM is actually the fastest form of volatile memory that we have deployed. And again, now it's relatively expensive. Since it's very, very fast, it's also volatile, just like DRAM. So you see it deployed in relatively small amounts, typically literally embedded inside of processors. So it's etched out on the circuitry just like the arithmetic logic is etched out. So that's by far where you see the most deployment of SRAM, is actually used as CPU caches.
Yeah, this is Scott. Just to add on to that a little bit, it comes down to scale and scaling capabilities. So SRAM is the largest cell. NAND provides the smallest cell, if you will, for a given bit, and that's why we see all these different technologies used, and hence why SRAM is not really sold today in large volume as a standalone component, is because of density versus usability.
Great, thanks, guys. And Jay, there's one other question. Do you have time for that, or do we want to wait till the end?
Go for it.
Okay. So the next one, again, is for Rob and Scott, is that does 3D NAND use multiple voltage levels, or does each layer just use 2 voltage?
So again, very good question. And the answer is it depends on the type of NAND design, be it MLC or TLC. Again, those are by far the most common as deployed in a 3D NAND architecture. So if you had a 3D NAND with MLC, every single cell would have 2 bits represented per cell. 3D NAND in TLC form, all the cells would be 3 bits per cell. So I don't know of any quote-unquote mixed designs. All the 3D NAND being produced today is one type or the other. And then again, in the future, who knows? I'll bet you we'll see 3D NAND in QLC form as well.
Great. Thanks,
yeah,
Rob.
and just to add a little more to that as well, and just to give some clarity, if you think about the concepts of the skyscraper, as Rob called it, and as we in the market do as well, you build apartment complexes for planar devices, and this is literally just stacking the apartments up to create a skyscraper. So the idea of a NAND string is going from being flat or planar on the silicon to just going vertical. It does bias back a lot of other things by doing that, but there are also further challenges. So yes, you do see a lot of different things going on with going to the 3D architectures, but to Rob's point, one of the benefits we get from going to 3D is the opportunity to make TLC and in the future QLC products viable.
Great, thank you, guys. So the only other question was real quick, is this presentation going to be emailed to us? It will actually be posted to the website. We have the updated, they're actually already up there right now, and we'll give you that link at the end of the presentation. So that said, I think we're ready to go, Jay.
Excellent, great. And I think that was probably a great time to ask those questions right off the heels of what Scott and Rob were talking about. So we've been talking about those different types of storage media, including memory and form factors and architectures. And yet, in order to place these things into context, we need to understand how to communicate with these devices. And Rob's talked about SATA and SAS and NVMe, and we're going to be focusing on the NVMe part of it, because this is where NVMe and NVMe over fabrics come into play. So you've probably heard about NVMe before, not just when Rob was talking. It stands for, you can see if you can tell the typo here on the slide. It stands for Non-Volatile Memory Express. That's a typo on my part, and it is corrected in the PDF slides. And I think there's actually going to be one more typo later on. I must have been thinking about different types of media as I was writing this out. But it stands for Non-Volatile Memory Express, and the SNIA definition defines it as a host controller interface with a register interface and command set designed for PCI Express-based SSDs. In other words, it's a fancy way of saying that it's a standardized protocol for allowing computing functions in a host to communicate with PCIe-based memory and storage, which happen to be non-volatile in nature. Now, it also happens to be that NVM Express also stands for the technical body that defines and standardizes the protocol as well. But for our purposes here, we're going to be focusing solely on the technology. So, what is NVMe? Moving into that definition just a little bit more specifically. Let's break it down a bit. A host controller interface is a piece of hardware or software that allows your CPU to talk with some type of memory or storage device. And as you can see in the graphic on the screen, very simplified, we have a CPU that communicates via PCIe with a storage device, which is called an NVMe subsystem. Now, when you make this connection, each vendor has a particular way of doing things. So without a standardized approach like NVMe, you have to run through specific hardware, firmware, drivers, qualification processes for each vendor. By using NVMe, though, there's a standardized register, feature, and command set, which makes it a lot easier for everyone in the long run. And one of the things that's notable about NVMe is that it's specifically designed for the types of technologies that we've been discussing today. As Scott and Rob outlined and illustrated, there are a lot of ways to architect non-volatile media. And you can imagine how difficult it can be to create specialized communication systems to reach them all. This way, however, we have an open industry consortium devoted specifically to making it as straightforward as possible to communicate with all the different types of non-volatile media. Now, the NVMe protocol itself is designed for being directly attached via PCIe, which, of course, is a very low latency bus architecture. However, just as history has a way of repeating itself, keeping storage inside of a server doesn't solve all the problems inside a data center. So there will come a point in time when we want to increase the scale and reach our storage out across a network. Now, while you can extend the reach of PCIe, though, it's not known to be a robust fabric architecture. And that's where NVMe over fabrics comes in. It's an extension of NVMe that we can run over a network fabric. And therein lies the difference between them, realistically speaking. So when we use the term NVMe in this context, we're really talking about the direct attached PCIe-based solutions. Now, if we're talking about extending NVMe over network, we're talking about NVMe over fabrics. Underneath it all, though, is the same NVMe architecture and methodology. In fact, it's best to think of NVMe over fabrics as an extension of the NVMe paradigm across the network. So what kind of network? Well, that's a great thing. There's a few to choose from. The initial NVMe over fabrics specification generally have the transports fall into two different camps. You've got the RDMA-based fabrics like Rocky, iWarp, and InfiniBand, and Fiber Channel. So the NVMe Express group is currently working on additional fabric technologies right now as well. So you will see some additional ones being talked about very, very shortly. So one of the things to keep in mind is that NVMe has two separate models, which is why we make a distinction between NVMe and NVMe over fabrics. NVMe as a PCIe-based protocol is memory mapped. What that means is that we use the same address space to address both memory and I/O devices, in this case the NVMe storage media. So when we access that memory space by the CPU, it can refer to a portion of physical RAM, but it also refers to the memory of the NVMe SSDs. NVMe over fabrics, on the other hand, is a message-based transport instead of shared memory. So for those of you who are more familiar with storage networks, these are going to feel very familiar. Unlike the PCIe transport, which is categorized as memory-based, where commands and responses will share the memory, fabrics has a message-based transport. So different transport mechanisms have different capabilities, and you will use them natively in an NVMe over fabric situation. Now, if you want to know more about NVMe over fabrics and NVMe, SNIA has done Bright Talk webinars on NVMe and NVMe over fabrics. This particular conversation about NVMe over fabrics is a Bright Talk webinar called Under the Hood with NVMe over fabrics. And you can do a search right now and find out that information at your leisure. So, let's take a look at the two of them side by side, because sometimes this can be a little bit more informative to see them side by side. So the top graphic represents what you'd see today in a PCIe SSD. You'll notice that there's a controller which manages the namespace on a particular non-volatile device. And it's typically a single controller with one or more namespaces in the device. As fabrics come out, you will see the implementations put on larger storage systems which are servicing more than one host, even potentially thousands of hosts. What you're seeing in the bottom diagram then is the scaling of these subsystem architecture elements and the elements within it. Now, the important thing to remember here is that the model stays consistent, whether we're talking inside of a host system or outside of it. In fact, you can see all of the different pieces of the puzzle in both systems. It just happens to be one is scaled and the other is more for smaller individual types of deployments. So ultimately, when we tighten the straps on all of the pieces of this puzzle, we can see where our data goes and how we get to it. NVMe and NVMe over fabrics are just the newest means by which to get there. And of course, as I said before, we do have additional longer-term webinars to go much deeper into both NVMe and NVMe over fabrics. And I highly recommend that you take a look at that if you have additional interest in that. But as far as we've been concerned here, this is the glue that keeps the different storage media and memory media together, both inside and outside of a host. And with that, I'll hand it back to Chad.
Thanks, Jay, Rob, and Scott. Phenomenal job today, guys. And hopefully we've managed to provide some new nuggets of information to you and teach you something new that you didn't know about these topics that we went over today. But from a high level, here's what we covered from a webcast perspective. So first of all, we went over volatile, non-volatile persistent memory and defined it and gave you different use cases. And it's really important to just understand the different factors in speed and volatility so you can make the right decision on which application you could use those in. Secondly, we went over the different form factors and we went through the alphabet soup and the acronym soup. And it's important that you choose wisely to select which one fits your use case. And lastly, Jay did a great job of going over what NVMe is, easy for me to say, and NVMe over fabrics and the different use cases around that as an extension to NVMe. So with that said, that's kind of where we've gone, but we want to make sure that as we move forward here, we're going to have more webcasts in this series. And our next one will be September 28th. And we actually don't have any questions from the audience to go over, guys. You guys did just such a good job going through the topics. I think you've answered most of the questions. But if there is questions that come up, we will post that. Did one come up?
Sorry, Chad. I do see a couple of
they're coming in. As I'm talking, they're coming in. Here we go. Okay, so let's go through. Here's one for Jay. When you see NVMe over Fibre Channel becoming mainstream, just a guesstimate. What's your thoughts?
We're getting some really good questions here, especially when it comes to the when, the hows, and the wherefores. So Fibre Channel is one of the transports that is specifically stated inside of the NVMe over fabrics. And the Fibre Channel industry has been making tremendous inroads as to getting these systems. The one thing about Fibre Channel that makes it valuable as a storage transport is the end-to-end qualifications. And when you buy Fibre Channel, you buy effectively a solution that works from the host all the way to the storage systems and all points in between. And the Fibre Channel version of NVMe is in the final stages of approval. In fact, as of this presentation, the NVMe Fibre Channel spec is going into its final completion next week. So by the time you see this video or you see this webinar, that specification will be completed and it will be a finalized, standardized technology. And so the rest of it becomes a matter of when the vendors will have a qualified, generally available products. And I would anticipate that to not take very long at all. They've been working on this for quite a while. So I think we're going to find some qualified Fibre Channel NVMe over fabrics relatively soon.
Great, thanks, sir. Another one that came in was how are networked NVMe SSDs addressed? Okay, so when we start to talk about NVMe and NVMe over fabrics, the NVMe SSDs, as the question is written, would be qualified as a PCIe approach. And the way that would work is effectively that the NVMe driver would identify and register a namespace to the host, which would then use it as its own part of its own memory mapped architecture. In other words, the driver itself would be the registration of the system. In a networked environment, for NVMe over fabrics, we would be using the NVMe system to have a port that is addressable on the network itself. So what happens is that the NVMe controller in the subsystem would have a port that you would address using Fibre Channel or Ethernet RDMA or iWarp or InfiniBand. So the port itself would be the address on the network, and that port would be connected into an NVMe subsystem controller, and that would be a one-to-one mapping between the controller and that port. And that's how you do it over a network. Great, thanks, Jay. One that came in for Rob and Scott is, other than real estate savings, what advantage does 3D NAND offer? Steve?
So I'll start with that, and then Scott can jump in. So there certainly 3D NAND for a given surface area is much more dense than its 2D counterpart because of the layering technique. No question about that. Now, some of the other maybe not so obvious advantages, I think, and Scott can chime in as well, is that because there are multiple layers, there are much more possibility to do provisioning of NAND blocks and pages to be more creative in things like error correcting codes, potentially actually higher performance, because now I have many more within the NAND itself, many more parallel paths to read and write across the layers, as opposed to just a single layer where I'm limited in the techniques that I can use. So 3D NAND actually has a lot of possibilities, especially as more layers are added to take advantage of more parallelism.
Yeah, and to follow on to Rob's comments, another significant advantage of the 3D NAND that is beneficial to the market is we use electrons to alter the state of the 0 or 1 or 0011 being stored. And at the scale that we were at with planar technologies, the number of electrons, literally the number of physical electrons that separated one of those given states of 00 to 01 was down to 16 electrons. That's very difficult to manage. When we get to the 3D architectures, that 20 nanometer or 16 nanometer gate measurement that we've used to measure the distance of a NAND cell goes away when we go vertical. We've re-architected these cells such that the amount of physical space used to store those number of electrons has substantially increased again. And by doing so, that means we have more electrons to use to separate out the different bit locations between the 0001 up to 11. And that's what allowed us to make TLC and potentially QLC become more mainstream, is it buys us physical XY dimensions, but as we go vertical in the Z as well, it allows us to expand the size of that used to be a 20 nanometer square of floating gate into something much larger, and why we stop talking about NAND in nanometers and we start talking about NAND in the tiers that Rob was mentioning. From a speed call out there, there's not necessarily a speed improvement, there's a speed maintaining aspect of it, because as we did go vertical, we introduced a bunch of different potential defect paths that had to be overcome compared to planar, but they've gotten to the point now where those are substantially more reliable, but it doesn't necessarily speed the device up. It's more of a reliability play than anything else.
Excellent. Thanks, guys. And one last one on NVMe. So does NVMe have any specific connectors like SATA or SAS?
I'm sorry, can you say the question one more time?
It says does NVMe have any specific connectors like SATA or SAS?
So when you're talking NVMe inside of the server, it's a direct PCIe connection, and so you basically put your NVMe SD into a PCIe slot on your server. And inside of a network, you would use the network card, whether it be a NIC or an RNIC for an RDMA NIC, an InfiniBand HBA or a fiber channel HBA. But there's no SAS or SATA connectors, which is one of the reasons why it actually is a more efficient protocol, because you don't have to go through an adapter to translate between what the CPU can understand and what the memory or storage can understand. So there's no SAS or SATA connectors in that form, no.
To add on to Jay's comments there as well, if you look at it from a physical external, how you connect it with the actual edge connection of the NVMe drive, if you will, the small form factor SFF working group does dictate what the pinouts of those connectors look like, and there is a unique connector that was designed around allowing NVMe, SATA, and SAS to share one physical connector to the server that you're installing, storage product you're installing it into. And it's been given the definition U.2 to be a universal 2.5-inch edge connector.
That's correct, yep.
Great. So with that, I think we've covered most all the questions, guys, and we still have a minute or two left here. So going into, like we mentioned before, we are going to continue this series. So if there's other terms that you need to have a better understanding, we're going to have our next webinar or webcast on September 28th. And it's going to be what we call SCIAN is the next one, and around storage management. And you can register. Hopefully I said that correctly. And so you can register at this link here. And if you've missed any of the ones that we had before, in Teal and Rose and all of those, they are all available here, and you can download the PDF and access the webcast and watch them on demand. Also, one of our most popular series is around storage performance benchmarking, and if you want to watch any of that, they're all available on demand at this link as well. So after this webcast, and this was asked earlier, we will have the PDF, and it's the updated one with that Jay was mentioned before. There was a couple of typos that were fixed, and they're updated, and they're up at this link, up at the ESF webcast link that's provided here. We will be hosting the Q&A with response from the presenters on the SNIA ESF blog. That will be up there as soon as possible. Please follow us on Twitter. Please rate this webcast and provide us feedback. We want to know from you what you want to learn more about from a storage perspective and how we can help you. So please send that information and rate the webcast for us. So with that said, thank you for attending today, and we look forward to seeing you and hearing from you in our next webcast on September 28th. Have a good day, everyone.
Please don't forget to rate.